Hello. In this lecture on demand, I will be discussing orbitals, specifically atomic orbitals in this case, although we will touch a little bit on molecular orbitals, and specifically hybridized atomic orbitals is what we want to focus on today. So, before we start, let's consider what are orbitals anyway. Well, this is a concept you're somewhat familiar with, and there are a couple different ways that we can think about orbitals. We sort of think of them as a place where electrons can be found, and it doesn't matter whether there's actually electrons there or not. We think of the orbital as being there because it's a place where the electron could be found. Remember, you can't put more than 2 electrons in an orbital, but it's sort of a shape where the electron is, so to speak, smeared out over the whole shape. It's actually a bit more accurate to say that it's the form that an electron wave may take, because electrons are tiny and moving very fast. They can be thought of as waves as well as particles, and as a wave it has to take on a certain shape or wave form, and so the orbital is kind of the shape that a particular electron has when it has a certain energy. And third, probably the most practical way of thinking about it is it's just a useful way of thinking about the properties of atoms and molecules. So let's talk about the kinds of orbitals. First of all, there are atomic orbitals and molecular orbitals. Atomic orbitals are located on a particular atom, as it makes sense because it's called an atomic orbital, and molecular orbitals are smeared out over 2 or more atoms, so they're called molecular orbitals. We won't spend much time with molecular orbitals in this particular lecture today. Now, under atomic orbitals, there are 2 kinds. Unhybridized, which are the familiar S, P, D, F, and so on that you learned about in general chemistry. And then there are hybridized atomic orbitals, which are combinations of S's, P's, and D's, and so on. The 3 that we're going to focus on are called SP, SP2, and SP3. Unhybridized atomic orbitals, again reviewing from general chemistry, are most useful when you're considering single atoms, unattached to any other atoms. Generally, atoms, when they're bonded to each other, will involve hybridized orbitals, so unhybridized ones are pretty much only for single atoms. And like with all orbitals, a particular atomic orbital, hybridized or unhybridized, can't have more than 2 electrons. That's a hard and fast rule that we learned in general chemistry. As for types of unhybridized atomic orbitals, we have the S, which is just a sphere. And remember that there are S orbitals in every level. There's one in the first level, there's another one in the second level, there's another one in the third level. They're all just spheres, and they just get bigger as you go up in energy levels. So the 2s is bigger than the 1s, and the 3s is bigger than the 2s, and so on. Now also notice about the S that it's a single lobe. It doesn't have any parts. So it's either a positive or a negative phase, but it doesn't have both. And there's no nodes in here because there's no dividing line within it. Unlike a p orbital, which has always 2 parts to it, a positive part and a negative part, you can consider whichever one you want to be positive and whichever one you want to be negative. These are not signs, these are wave phases. Just like a wave may have a crest and a trough, these kinds of waves have positive and negative parts, and it has so these are lobes, and it has a node in the middle where there is no or very little electron density. Also, don't forget that there are 3 p orbitals in each energy level above the first. The first level doesn't have any p's, but the second one has 3 of them. The third one has 3 more, bigger p orbitals. The third energy level has 3 more p orbitals, even bigger than the first ones and the second ones, and so on. And then there are d orbitals as well. These are a couple kinds of d orbitals. There are 5 in each level above the second, not in the first or the second, but in the third there are 5 d orbitals, and so on. We're not going to worry too much about d orbitals, so mostly we're going to focus on the s's and the p's. Okay, and also don't forget that they go in order of from lowest energy to highest energy. And when we're talking about energy, what we really mean is how much energy does an electron have when it's in a particular orbital. So the lowest energy it can have is when it's in the 1s. If it's in the 2s, it's a little bit higher in energy. If it's in the 2p, it's higher yet, and so on. In the order you learned in general chemistry: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. There's a number of ways you can remember that. Probably the easiest is just to look at the periodic table. Okay, now let's talk about hybridized atomic orbitals. By the term hybridized means that we're going to combine 2 things, like a hybrid variety of corn has 2 different or more than 2 different kinds of corn hybridized into one, or a hybrid dog is collie and German shepherd is a hybrid of both. Well, a hybridized atomic orbital is formed by combining 2 or more unhybridized atomic orbitals. And this is important. This is a very useful thing to keep in mind. The number of hybridized atomic orbitals produced equals the number of unhybridized atomic orbitals used to produce them. So if you're going to combine two unhybridized orbitals, you're going to have to make two hybridized orbitals. And if you're going to combine three, you're going to have to make three, and so on. And like with all orbitals, a hybridized atomic orbital holds two or fewer electrons, no more than two. We will learn what sp, sp2, and sp3 means here in a few minutes, but just to give you a clue about the energies, the hybridized atomic orbitals, whether they're sp, sp2, or sp3, are always between the energy of an s and the energy of a p, which makes sense since they are made from s's and p's. They're kind of combining an s and a p. They're going to be somewhere in between in terms of energy. And if you're comparing the three, an sp3 orbital or an electron in an sp3 orbital is always higher in energy than that in an sp2, and that's higher than in one in an sp. So if there are any unhybridized p orbitals left over, which we will see there are in some cases, the unhybridized p atomic orbital left over is always higher in energy than whatever hybridized orbitals you might have made. Okay, so let's be specific now. Let's look at sp3 hybridization. sp3 hybridization comes about by combining an s and all three p's in a particular energy level. Now obviously this can't happen in the first level because there are no p's, but in the second level or the third or above you can do this process called hybridization. sp3 specifically involves the s and the three p's from a particular level. Okay, so what we're going to do is combine the s and all three p's as indicated by this box, which extends over the s and all three p's. And how many new orbitals are we going to make if we combine an s and three p's? That's a total of 4. We squish them together, we throw them back up on the board, and how many new ones will we make? 4. However many old ones you start with, that's how many new ones you have to make. So we'll make 4 new ones represented by these 4 boxes, and notice that now, unlike these, where they're different from each other, these 4 are all the same as each other. And they're all called sp3 because they're all the same. They're all the same energy as each other. What does an sp3 orbital look like? Well, it looks like this, kind of like a p orbital, in that it has 2 parts, a positive phase and a negative phase, and a node in between. But notice that one part is big and the other part is little. Right, so we refer to this as the big fat part. And because there are 4 of them in an atom in a particular energy level, there are 4 sp3 orbitals, assuming that it's sp3 hybridized. And I'll tell you in a few minutes how you determine if it's sp3 hybridized or not. But if it is, then we have to have 4 of them. We have to see how would they all be arranged with respect to each other. Well, this is how they're arranged. The 4 orbitals are oriented tetrahedrally to each other. In other words, 109.5 degrees away from each other. That should look familiar. It's essentially the tetrahedral electron group arrangement. Let's move on to the sp2 hybridization. How does that happen? Well, in this case, we're going to again start with the s and 3 p's, but we're only going to combine the s with 2 of the p's, not with all 3. So this box that says sp2 hybridization just extends over the s and 2 of the p's. That one is not affected. So we're going to take 3 old orbitals and we're going to make how many new ones? 3. And they're each called sp2. They're all the same as each other. But that p orbital that was not hybridized here stays there. It can't just disappear. So there's still the p, and it's higher in energy than these 3 sp2s. What does an sp2 orbital look like? Well, interestingly, it looks pretty much like an sp3 orbital. A big part and a little part, a positive phase and a negative phase, a node in between, these 2 lobes and a node in between. And how are these 4 orbitals, 3 sp2s and a p, oriented with respect to each other on an atom? Well, the 3 sp2s, here, here, and here, are arranged trigonal planar. In other words, 120 degrees away from each other, all in the same plane. The p orbital that was unhybridized is still there, but it's perpendicular to the plane of the other 3 orbitals. Now, it's really important to notice that there are still 4 orbitals here. That's an orbital called sp2. That's an orbital called sp2. That's an orbital called sp2. This is 2 parts, but it's all 1 orbital. Now, you might ask what happened to the little tails on the ends of these fat pieces, and I will tell you they're still there. It's just that we didn't put them in the picture because it makes it look too complicated. So remember that the little tails on each of these sticking out from the hind end, so to speak, of each one. So they're all crowded in there in the middle. But to keep it simple, we don't draw them in. It's just simpler to not draw them. Okay. Now let's back up to the sp3 for a minute and ask ourselves, now assuming that this is an sp3 hybridized atom, what atom is it? Is this carbon? Is this nitrogen? Is it oxygen? In fact, it can be any of those. It really doesn't matter. But depending upon which atom it is, that's going to determine how many electrons there are in here. So if this is carbon, then there are 4 valence electrons, and there'll be 1 in each of these places, and there'll be 1 in each of these boxes. If it's nitrogen, there's 5 valence electrons, so there'll be one here, one here, one here, and two here, or it really doesn't matter. You could put the pair in any one of these four and the other three single electrons in any of these places because they're all the same as each other. And of course that would be represented by two arrows, one up and one down, one arrow, and one arrow in the boxes. Same thing is true when we talk about sp2. Is this a carbon, a nitrogen, or an oxygen, or whatever? Well, it depends. If it's carbon, then there's 4 electrons. There'd be one in that orbital, one in that orbital, one in that orbital, and one in that orbital. If this were nitrogen, there'd be 5. There'd be 5 electrons in these 4 orbitals. 1, 2, 3, 4, and then we go back and pair up one of these 3. If this were oxygen, there'd be 6 altogether. 1, 2, 3, 4, plus we'd pair up 2 of them in that orbital and 2 of them in that orbital. Or again, it doesn't matter where the pairs are as long as we have 2 with pairs, one with a single electron and another one with a single electron for oxygen. If it's halogen, total of 7 electrons, we'd go 2, 4, 6, plus 1 in that one would be 7. So you see it's not the fact that it's sp2 that determines what the atom is or vice versa. It's the number of electrons that go in that determine what the atom is and vice versa. Now let's move on to sp, the third kind of hybridization. As you might guess, that involves taking the s orbital and one of the 3 p orbitals from a particular level, again normally the second energy level, combining them, and since we're starting with 2, how many are we going to make? 2 new ones. The 2 p orbitals that we didn't use in doing the sp hybridization are still there unhybridized, so we have 2 sps and 2 p orbitals. This is what an sp orbital looks like. Not too different. It's pretty much the same as an sp2 or an sp3 orbital. Again, a little bit of difference maybe in the relative size of the 2 pieces, but there's a big piece and a little piece, the positive part and a negative part, lobe, 2 lobes, and a node in between. How are they arranged on an atom? Well, this looks a little funny the way I've drawn it here, so bear with me here for a minute. This is an sp orbital pointing out this way. This is another sp orbital pointing out exactly 180 degrees from each other. In other words, the 2 sp orbitals are oriented linearly 180 degrees away from each other. And then, so that's an orbital, and that's an orbital, and then the 2 p orbitals that are left over, unhybridized, one points straight up and down, perpendicular to the other 2 sp orbitals, and the 4th orbital, the second of the p orbitals, also points perpendicularly to everything else, and that's hard to draw on a 2-dimensional surface, but essentially I have one straight up and down, one straight in and out, one pointing that way, and one pointing that way. That's how an sp hybridized atom looks. Again, that's going to be true whether it's carbon, nitrogen, oxygen, or whatever. If it's sp, this is what the picture is going to look like. The only difference, as we've seen, between different atoms would be how many electrons go in. So if it's carbon, there'd be 1 electron in each of the 4 orbitals, one there, one in this orbital, and one in this orbital. In other words, 4 single electrons in the 4 boxes. If it's nitrogen, we'd have 5 valence electrons, so perhaps 2 in that one, 1 in that one, 1 in that one, and 1 in that one. So 2, 1, 1, and 1. If it's oxygen, we'd have a total of 6, so 2 here, 2 here, 1 there, and 1 there. So 2, 2, 1, and 1. And if it's halogen, 2, 2, 2, and 1, 2, 2, 2, and 1. Again, notice that there are a total of 4 orbitals here. It looks like 6 pieces, but actually this is all 1 orbital, this is 1 orbital, but this is all 1 with 2 parts or 2 lobes to it, and this is all 1 with 2 lobes to it. Let's back up to the sp2. Again, 4 orbitals, 1, 2, 3, 4. And let's back up to the sp3. Again, 4 orbitals, 1, 2, 3, 4. In every case, in hybridized atoms, sp, sp2, or sp3, since we're starting with a total of 4, we have to have a total of 4 in the balloon picture. Now, just to reiterate, remember, oxygen may be sp, sp2, or sp3. Nitrogen may be sp, sp2, or sp3. Carbon may be sp, sp2, or sp3. Halogens may be sp, sp2, or sp3. In other words, what atom it is affects the number of electrons in the various orbitals, but not what the hybridization is. So any atom can be any hybridization. So then you may be confused and you may be saying, but how do I know what the hybridization is? Do I have to predict that? And the answer is yes, it's very easy. You simply look at the atom and you ask yourself, is this tetrahedral? Is it trigonal planar, or is it linear? If there are 4 groups, it's tetrahedral, being automatically sp3. If it's 3 groups, we know that it's trigonal planar, being sp2 hybridized. And if it's 2 groups, we know it's linear, being sp hybridized. Now, you may be wondering, may have occurred to you, but we had 2 more electron group arrangements from Gen Chem. we had trigonal bipyramidal, and we had octahedral. Well, those are yet different hybridizations. They involve d orbitals. We're not going to worry about it here for Gen Chem. So really it's just these three. Every atom that we deal with, for the most part, will be tetrahedral, trigonal, planar, or linear, sp2, sp3 hybridized, sp2 hybridized, or sp hybridized.